watched a video and wished it could just explain itself? Not just with words, but by literally pointing out who's doing what and where. Well, that's exactly what the Grove model is here to do. Imagine an AI that not only describes what's happening in a video, but also tracks objects over time, even when they disappear behind the scenes. Grove's secret? A massive dataset, How to Ground 1 Million, built using a clever AI-powered pipeline that turns scattered frame-by-frame descriptions into smooth, consistent captions, grounded in reality. Today, we're diving deep into how Grove learns to see and tell with unprecedented accuracy, and why this might just be the future of video understanding. Let's break it down.
This paper introduces a new approach for generating captions for videos, while also identifying and localizing key objects. The real challenge isn't just describing the scene in natural language, but tracking objects across time. If an object changes size, disappears, or reappears, the model still needs to keep the bounding boxes consistent. Sound tough? It definitely is. How do the authors tackle this? They propose 3 main contributions. First, they introduce an automated way to generate training data using the How to 100 million inches dataset alongside an object detection model and an LLM. From this process, they create a new dataset called How to Ground 1 million. Second, they present iGround, a new dataset of 3,500 manually annotated videos containing dense object grounding and captions. And third, they build a model called Grove, which is pre-trained on How to Ground 1 million and then fine-tuned on iGround. They show that Grove achieves state-of-the-art results on vid, STG, and ActivityNet entities. Look at Figure 1 to see Grove in action. Example. In that example, a woman stirs food in a wok with a spatula. The generated caption describes this activity, and color-coded bounding boxes highlight the key objects. Even when an object is briefly out of view, the model stops drawing a box, then restarts when the object appears again. That sets the stage for how the authors tackle the large-scale data challenge. A major obstacle in grounded video captioning is the lack of large-scale training data. How do we fix that? The authors introduce 2 new datasets. First, they automatically generate How to Ground 1 million from the massive How to 100 million inches dataset. This uses an existing object detection model and an LLM to create captions with consistent object bounding boxes. Then they introduce iGround, a smaller but manually annotated dataset of 3,500 videos and over 230,000 bounding boxes. Although iGround is smaller, it has carefully curated, high-quality labels. They then describe Grove's core contributions. It learns spatio-temporal grounding, meaning it captures how objects move or appear across a sequence of frames. It uses a video-based decoder to ensure bounding boxes remain consistent, and it includes a component to handle occlusions and disappearances. Grove is pre-trained on How to Ground 1 million, then fine-tuned on iGround. Check out Table 1 to see how these new datasets compare to existing ones. Notice How to Ground 1 million dwarfs most other datasets in size, while iGround offers more detailed annotations. The authors also discuss related work, highlighting the difficulty of manually labeling video grounding data and how automated pipelines with pre-trained models, including LLMs, can massively scale up the creation of high-quality datasets. Now that we have a sense of the data setup, let's explore how they generate high-quality captions in the first place. Generating captions that also localize objects consistently over time is tricky. If you only use individual frame-based models, you might get slightly different descriptions for each frame. Imagine calling something a beverage in one frame and a green drink in another. That inconsistency makes it hard to keep track of the same object. So the authors propose a 3-step method. First, they caption frames separately. It's not perfect because each frame is handled on its own, but it's a start. Second, they feed those captions into an LLM to produce one unified description of the entire video. During this step, they extract structured triplets, who does what to whom, and align them so that objects and actions stay consistent. Third, they fix object bounding boxes so that they actually track the same object over time. The final result is a single caption describing the video and bounding boxes that remain stable across frames. Look at the figure here, which breaks down each step. You can see how the language and visual tracking get merged into one consistent output. Pretty neat, right? But having a method to unify frame-based captions is only one part of the puzzle. Next, we'll see how the authors handle temporal labeling of objects on a large scale. Keeping track of objects across frames is essential, If the model can't consistently label the same object through a sequence, you'll see bounding boxes flicker in and out. To fix this, the authors propose temporal labeling of objects. Instead of treating each frame in isolation, they teach the model to recognize noun phrases in the unified caption and label the corresponding objects across frames. They then scale up training by applying this automatic annotation approach to how to 100 million inches, creating how to ground 1 million. This dataset has millions of captions, noun phrases, and bounding boxes, making it the largest of its kind for grounded video captioning. So how does Grove use this data? Caption. It takes in a sequence of frames and a natural language caption, then outputs spatio-temporally grounded bounding boxes. It also introduces spatio-temporal adapters to stabilize learning. And there's a bounding box decoder to refine the final boxes so they stay aligned with the caption. Even when objects disappear or get occluded, the model learns to handle that gracefully. This method turns disconnected snapshots into a coherent, robust narrative. But what if objects move in and out of the frame a lot? Let's see how they deal with that next. One common headache is when objects pop in and out of view. Ever watched a video where someone is washing a dog and the dog moves out of frame for a second? If the model doesn't track that correctly, bounding boxes will keep appearing and disappearing randomly. To prevent this, the authors add a temporal object-ness head. This component predicts whether an object is actually visible in each frame. If it's occluded, no bounding box is drawn. They also use spatio-temporal adapters to keep object representations stable as time progresses. Rather than reclassifying objects from scratch in each frame, these adapters help the model realize it's the same object from one moment to the next. Grove then uses two encoders, one for the overall scene and one for grounding specific objects. The model combines these signals to generate video prompts, which the LLM turns into structured captions. Each noun phrase in the caption aligns with a bounding box. Peluit. Check out iGround, the 3,500 video dataset they introduce here. It's carefully labeled so that each bounding box matches a short phrase in the caption, focusing on active objects, ones people interact with. Business. This dataset is split into training, validation, and test sets for a fair evaluation. Next, the authors move on to experiments, assessing how well the model's predictions match ground truth captions and bounding boxes. So how do we measure a grounded caption's success? It's not enough to generate a caption that sounds nice. We also need to verify that the noun phrases actually match the right objects in the video. That's where the experiments come in. Check out Table 2 to see how Grove compares to other methods on iGround. Notice how the two-stage strategy, pre-training on how to ground 1 million, then fine-tuning on iGround, consistently gives better results. Performance metrics like Meteor and Cider look at caption quality, while AP50 and Recall check the accuracy of the bounding boxes. Grove outperforms a baseline that relies solely on automatic annotations. They also test on vid-STG, shown in Table 3. While Grove performs well, some specialized models for vid-STG still hold an edge in certain metrics, indicating there's room for domain-specific improvement. Finally, they evaluate on ActivityNet entities in Table 4, where Grove shines with the best performance among all compared methods. A key takeaway? Large-scale pre-training is powerful, but fine-tuning on a smaller, high-quality dataset really pushes performance forward. Next, let's look at how Grove behaves in more qualitative, real-world examples, and see what happens if we tweak different parts of the model. Here we get a closer look at how Grove performs in actual video scenarios. Look at Figure 4, where you'll see full captions along with bounding boxes for objects like spoon or bowl. The bounding boxes remain stable over time, which is exactly what we want. Still, there are occasional mistakes. One example shows the model labeling an item as yarn, which doesn't exist in the scene. It's a reminder that no system is perfect. Then check out Figure 5, which shows how performance scales with different dataset sizes, ranging from 1,000 to 1 million videos. You can see improvements across metrics like Cider, AP50, and Recall as the amount of pre-training data increases. But notice how fine-tuning on a quality dataset is crucial. Just throwing more data at the model helps, but it won't match the results you get when you refine it with carefully labeled examples. The authors also conduct an ablation analysis. They train smaller versions of the model to test how much each component, like spatio-temporal adapters or bounding box refinement, contributes to the final score. Turns out, each piece matters. So how do we confirm which ones matter the most? Let's check that now. Fine-tuning a model isn't about blindly tuning every knob. It's about focusing on the parts that really matter. Table 5 shows what happens when you remove spatio-temporal adapters or freeze certain layers. Performance drops. This confirms that letting the network learn object tracking across time is critical. Now look at Figure 6, which explores the temporal objectness threshold. A higher threshold reduces false positives, but might cause some valid objects to be missed, so it's a trade-off. Meanwhile, Table 6 compares alternative annotation approaches. Some methods produce decent captions but struggle to ground objects accurately. Others ground objects well but don't generate strong captions. Grove strikes the best balance by enforcing both frame-level and video-level consistency. All in all, the conclusion is pretty clear. Large-scale pre-training sets the foundation, while careful fine-tuning with high-quality data is what really pushes Grove to the top. Thanks for joining us today. Happy exploring!